Hi everyone, this is lesson 5.3 and it's on residential mortgages in Canada. So this lesson is going to bring together several concepts, ones we talked about in Unit 5 and also ones that we've talked about in previous units. And it's going to be a more real-life example of where you will see annuities in practice. So looking at the amortization schedules we've done, looking at final payments, looking at all those factors, they all come together when you look at something that will probably affect the majority of you as you move on after college. So a mortgage, in fancy terms, is a claim to a residential property given by a borrower to a lender as security for repayment of the loan. Basically, okay, the lender gives you a loan and they have a claim to that property that you're using the loan to pay for, in this case, for most instances, a house or a condo. And as part of that, that loan is called a mortgage. And there's two major types, a fixed rate and a variable rate mortgage. There's more kind of subcategories we're going to go in as well. A fixed rate, as the name suggests, has a fixed rate of interest, okay, for the term that you pick, okay? So most mortgages, the maximum length you can have in Canada is 25 years. But that's the total term for the mortgage, meaning if you buy a house for $200,000, that's the whole term, that at the end of the 25-year period, you've paid off that $200,000 mortgage plus the interest. When you talk about fixed and variable rate, this is talking specifically about the interest rate, and they have terms. So a lot of times you'll see if you go to a bank's website, whether it's Scotiabank or RBC or CIBC, they'll give you mortgage rates that are fixed or variable, and they'll be for a certain number of years, 2 years, 3 years, 5 years. And you'll start to see that the longer the term is, the higher the interest rate. And that's because, especially with a fixed rate mortgage, you're guaranteed that rate of interest that you get the day you sign it for that period of time, whether it's 2 years or 3 years. Usually you don't go above 5 years in a lot of fixed rate mortgages. Variable rate mortgage, those are the opposite. So they don't have a fixed rate of interest. They actually will go up and down based on market conditions. So as the Bank of Canada adjusts its prime rates, it'll increase or decrease your overall mortgage rate. Okay, so it kind of tracks the market as opposed to locking you in to a fixed rate of interest. Okay, so similarly, when you sign up, you can get a fixed or a variable rate term for your interest rate. But for your mortgage, you can get a closed mortgage or an open mortgage. Okay, so a closed mortgage, you have your payments that you make. It's for a set period in time, and you make those payments whether it's monthly or bi-weekly. And you have restrictions where you can't make additional payments or change your terms very easily. An open mortgage allows you to actually repay the mortgage at any time or repay portions. In other words, increasing your payments or making additional payments. So they'll have clauses in there that will allow you every so many payments, you could double up your payment and pay double. Okay, and what that's doing is it's decreasing the amount of payments you have later on, so you're paying your mortgage off faster. Okay, a lot of people like open mortgages, especially if they have professions where their income can fluctuate. So if you can go from, let's say you have commission basis, you can have better months than others. You might be able to double up on mortgage payments that month. Okay. Whatever mortgage you choose, you're required to pay at least 20% of the loan. Okay. And when I say required, I mean if you do put down 20% of the down payment, so let's say your house is $100,000, that means you have to pay 20% of that. So you multiply that by 20%. It means you have to pay $20,000 up front in order to get that mortgage. If you do not, okay, then you have to pay mortgage insurance. So if you decided to only put 5% down or 10% of your mortgage, of your cost, or your overall loan down, So in this case, $5,000 or $10,000, if we go back to the $100,000 example, then what gets added to your mortgage is the cost of mortgage insurance. And that just prevents you from defaulting, or in other words, if you aren't able to pay back the loan, it's insurance to ensure that that money gets paid back, okay? So what I'm going to talk about in this, that was an overview of mortgages. And I'm going to go through a couple different examples looking at different mortgage options. And before I do that, I'm going to run you through a few steps, okay? So in Canada, the interest rate has to be calculated either annually or semi-annually, okay? So just like we've done in the past, those are typically nominal interest rates. You remember that was the factor J. So you have to convert them to an equivalent rate of interest. Remember, the equivalent rate of interest was based on the periodic rate of interest and the ratio C. Remember, C is equal to the number of interest payment periods per year, interest compounding periods per year, divided by the number of payment periods per year. Okay, so you have to find this equivalent rate of interest, because when you make your mortgage payments, you're not going to make them annually or semi-annually. You're going to be making those payments weekly or bi-weekly or monthly, usually. Okay, so that means that ratio will kind of fall into a typical pattern. What we will see a lot is the ratio being semi-annual for interest, or 2, and your payments being monthly. So if you have 2 divided by 12, you'll see in a lot of examples that actually is 0.1666 as a repeating decimal. Okay, so that's why I wrote 0.16 bar. So you'll kind of see these common ratios as we do examples looking at mortgages, and that's just because of the nature of how interest is calculated. Okay. So let's look at an example. I want to give you a refresher on doing effective interest rates. Okay, so this goes back, I believe, to Unit 1. Okay, so it's your first unit. And all we're trying to do is look at interest rates and figure out what your effective, or in this case, the other way to describe it, like I did, was equivalent interest rate is. Okay. The reason for that is, as you saw, with payments being something like monthly, and interest being either annual or semi-annual, that means that for all of these mortgages, they are ordinary general annuities typically. Okay, that means you pay at the end of the period, and the interest compounding frequency and payment period frequency are not the same. So let's take a look at an example. Suppose a financial institution posted the interest rates for their closed mortgages shown below being right here. Interest is compounded semi-annually, and mortgages require monthly payments. So what is the effective, or you can also call it equivalent rate of interest? In this case, it's the same, on a 3-year term or on a 5-year term. Okay, so remember our formula that we start with. You can call it effective rate of interest, you can call it equivalent rate of interest. Either one of those terms will work. Just remember that this formula is the same. P, which is the equivalent rate of interest, is 1 plus the periodic interest rate to the exponent C minus 1. Okay? And what will change in this question is not the ratio, but the actual periodic interest rate. Because remember, we're looking at either a 3-year term or a 5-year term. And as I mentioned, as you are going for a fixed rate, as you go for a longer term, your interest rate increases, okay? And that's just to that's how the bank can safeguard against sudden increases in interest without losing too much of that revenue, okay? So if interest rates look very good for kind of a medium outlook, then you might want to take maybe 3 or 5-year terms, or if you know that interest rates might drop, maybe you'll take a 1-year term, okay? But let's look purely at an example. So in example A, we're looking at a 3-year term. Okay, so remember our formula. P is equal to the 1 plus I to the exponent C minus 1. So in this case, our nominal interest rate provided here is 4.55%, which converted to a decimal is 0.0455. We were given in the question that interest is semi-annual, and that's the case for all of these interest rates. Okay, remember, going back to my previous slide, it's either going to be compounded annually or compounded semi-annually when we talk specifically about mortgages. So your periodic interest rate is I is J divided by M, or 0.0455 divided by 2. And if you calculate that out, you get 0.02275. Okay? Your ratio, again, your ratio is going to be the same for both Part A and Part B. And that's because, given in the question, interest is always compounded semi-annually, and you always have monthly payments. Okay? So remember, your ratio C is your number of interest compounding periods per year divided by the number of payment periods per year. And in both examples, the only thing that changed was the interest rate. So the ratio will be consistent for both questions. So your interest is semi-annual, which is 2, and your payment period frequency is monthly, which is 12. So again, that comes out to 0.16 bar, or in other words, 0.1666 as a repeating decimal. Okay, so substituting these values in, we get P is equal to 1 plus our periodic interest rate, 0.02275, to the exponent, 0.16, again, as a repeating decimal, minus 1. And our equivalent rate of interest in this case is 0.003756, which if you wanted to convert that to a decimal, remember you multiply it, or to a percentage, sorry, you multiply it by 100%, it would be 0.3756%. And you'll notice that is how I place the answers at the bottom in percentage. Okay, you can place it in either answer for me on a test, and that's completely acceptable. B is a 5-year term. So the only thing that changes, the formula is the same. P is equal to 1 plus the periodic interest rate I to the exponent C minus 1. And remember, your ratio stays the same. Okay, because it doesn't matter what your term is. Interest is always compounded semi-annually, and mortgages require monthly payments in this question. Okay? But what does change is your nominal interest rate, because for a 5-year term, your nominal interest rate J is 5.85%, which converting to a decimal is 0.0585. M stays the same, okay? Your number of interest compounding periods, semi-annual, which is 2. So I, the periodic interest rate, is J divided by M, which is 0.0585 divided by 2. Or in other words, I is 0.02925. So if I substitute these values in, I get that the equivalent rate of interest P is 1 plus 0.02925. To the exponent 0.16 bar, again, it's a repeating decimal, 0.1666, continuing forever, minus 1. So our value for the equivalent interest rate P is 0.04817, which again, if you want to convert that, okay, to a decimal, or at 4817, times 100%, you get 0.4817%. Okay? So again, this basic formula, and this is just kind of a refresh into how to do this, because you'll see that this will be something that you're going to have to do commonly in these mortgage style questions. So now that we've done a refresher on the effective rate of interest, you can also call it the equivalent rate of interest. That's what we have to use to calculate our mortgage payment. Again, because mortgages are ordinary general annuities, okay? Because the compounding frequency and payment period frequency are rarely, if ever, the same. And that's because, like I said, interest compounding always has to be annual or semi-annual, okay? And payments are usually more frequent, monthly, bi-weekly, etc. So to calculate the payment, it's pretty straightforward. We've been doing this 20, 30, 40, 50 times already in this course, where we're talking about payment using an ordinary general annuity. So we start with our present value, okay, which is how much you are trying to get in this mortgage or how much you're trying to get in a loan to buy a house or a condo. And the equivalent rate of interest, P. Okay, so in this case, we're looking at calculating mortgage payments. So when you look at calculating payments, it's over the entire mortgage length. Okay, so 20 years or 25 years. The term of your interest, let's say you have a fixed 5-year term, remember from our last example, that doesn't matter in this piece. What you're going to see is when we talk about balances after we look at payments, you're going to see why knowing the 5-year term is important. Because what happens is when your term is up for your mortgage, let's say this 5-year term's up, close to the end of it, you have to refinance your mortgage. So an item you might need to know is what your mortgage balance is at that period in time when you go to refinance. Okay, so two separate entities here. When you're looking at calculating your payment, okay, you have to take it over the entire course of your mortgage. Okay, so let's look at an example of this. So a mortgage for $120,000 is amortized over 25 years. Interest is 4.15% per annum, compounded semi-annually for a 5-year term, and payments are monthly. So what is the size of the monthly payment? Okay, so again, we're looking for payment, and like I said, because the interest compounding frequency and payment period frequency are not the same, interest is semi-annual, payments are monthly. This is an ordinary general annuity. So we use the payment formula for an ordinary general annuity, knowing the present value, because that's the 120,000 is how much we are getting for the loan today. So our payment is equal to our present value, again subscript G for an ordinary general annuity, times our equivalent rate of interest, divided by 1 minus 1 divided by 1 plus the equivalent rate of interest, P, to the exponent n. And again, this n, for the purposes of payment, is the total number of compounding periods for the entire mortgage period. So looking at our sidebar, that I always do on the right, present value is 120,000. Our nominal rate of interest, J, is 4.15%, which converting to a decimal is 0.0415. Our number of interest compounding periods, M, is semi-annual, so it's 2. So our periodic rate of interest, I, is J divided by M, or 0.0415 divided by 2, which if you calculate that out, you get 0.02075. The next item we need, okay, is our ratio C. That's the number of interest compounding periods per year divided by the number of payment periods per year. In this case, interest is semi-annual, or 2. And our number of payment periods, payments are monthly, so it's 12. So it's 2 divided by 12, which again, like I said, you'll get used to seeing this number for the ratio a lot. That's 0.16 as a repeating decimal, so 0.166666, continuing forever. So with this information, we can now calculate our equivalent rate of interest, P, and that's equal to 1 plus the periodic interest rate, I, to the exponent C minus 1. In this case, 1 plus 0.02075 to the exponent 0.16, again as a repeating decimal, minus 1. And we get an equivalent rate of interest, P, of 0.003429. Okay? Our last item, N, okay? In this case, it's payments is for the entire term of the mortgage, so 25 years, not the 5-year interest term. That's going to come in later when we look at calculating future mortgage balances. So N, in this case, is 25 years times 12 payments a year, which comes out to 300. So we can calculate our payment now. Our payment is equal to our present value, 120,000, times our equivalent rate of interest, 0.003429, divided by 1 minus 1 divided by 1 plus the periodic rate of, or equivalent rate of interest, 0.003429 to the exponent 300. Okay? If you calculate these numbers out, your payment should come to $411.48 in the numerator, divided by 0.6419, where you get an answer of $641.03. Okay, so that is your payment over the entirety of the mortgage, and that's assuming an interest rate of 4.15%. But again, what we look at in this question is that was for a 5-year term. So now, what I want to look at in the next couple of examples is how you look at refinancing your mortgage at the end of this term when the interest rates start to change. Okay? So as you can see, we're starting to piece together all the items that we've done within multiple units in this course. And they all kind of come together in a real-life application of mortgages. Okay? So at the end of your interest term, what we're going to do is we're going to figure out what the balance is in your mortgage. Okay? And that is so that at that period in time, you can refinance your mortgage and it'll be a new interest rate, either higher or lower, depending on how the market conditions have changed. So if you remember back a couple lessons ago, we talked about finding the final payment. Okay, and I had you a list of steps to do that. This is very similar. Okay, so there's 3 steps that you have to follow. What you have to do is you have to take the full value of your mortgage. So if you think back to the previous example, the $120,000, and you have to find the future value of it at the end of your term. Okay, so if you remember from the previous question, the interest term was 5 years. So if you start and you look at drawing a graph, we're here today. The mortgage was 25 years, and our interest only goes to year 5. So our mortgage started here at $120,000, and now we're trying to find the value of that whole mortgage piece at the end of our interest term, so 5 years down the road. And we do that using simple compound interest. In this case here, P is still the equivalent rate of interest, but N is the number of compounding periods for the term only. Okay? So in this case, it was a 5-year term. So that number of compounding periods is based on a 5-year term only, not the entirety of the mortgage, right? Because we're only going ahead a little bit into the future of this mortgage to look at refinancing, okay? Similarly, what you have to do is use the annuity formula in your second step and find the future value of all those payments that you made. So in our previous example, payments were $641.03, and you're going to make a certain number of them during this 5-year term. So this is simply using the future value for an ordinary general annuity to figure out what all that money you've paid in 5 years is worth at the end of that term. Then what you do is you simply subtract one from the other. Okay, so you have this future value, okay, and you simply subtract step 2 from step 1. So this actually becomes the value you obtained in step 1 minus the value you obtained in step 2. So I'm going to go through 2 examples of doing these steps just so you can kind of see how much or how to calculate that mortgage balance before we go on to something a little more detailed. So I'm going to start off as my first example doing the exact same question that we just did in example 2, but looking at the balance at the end of the term. So again, the question's the same. A mortgage of $120,000 is amortized over 25 years. Interest is 4.15% per annum, compounded semi-annually for a 5-year term, and payments are monthly. Monthly payments are $641.03. What is the balance at the end of the 5-year term? So you'll notice, if you remember back, that was the value we obtained in example 2. So we're going to go through each of these steps. Remember, there were 3 steps to follow. Okay, the first step was to find the future value of the full value of the loan. the $120,000. So that's simply compound interest. Future value is equal to the present value times 1 plus the equivalent rate of interest to the exponent n. Okay? So, in the second step was to calculate the future value of the annuity, assuming you had all these payments of $641.03 for the 5-year term. Okay? So the future value, again, these are general annuities, is equal to the payments times 1 plus the equivalent rate of interest P to the exponent n minus 1 divided by the equivalent rate of interest P. So those are your two steps. So the reason I showed both is I'm going to do our sidebar, and you're going to see that we're going to have all of the information when we do it there in order to substitute it into both equations. Okay? So starting with what we know, our present value is $120,000. Our nominal rate of interest J is 4.15%, which converting to a decimal is 0.0415. Interest is compounded semi-annually, so M is 2. So our periodic rate of interest I is J divided by M, or 0.0415 divided by 2. Okay? And that gives you 0.02075. Next, our ratio C, okay, the number of interest compounding periods per year divided by the number of payment periods per year. Interest is semi-annual, which is 2, divided by our payments, which was given in the question as monthly, so 2 divided by 12. Again, 0.16 with a bar, in other words, as a repeating decimal, so 0.1666, continuing on. So our equivalent rate of interest P is 1 plus the periodic rate of interest I to the exponent C minus 1. In this case, P is equal to 1 plus 0.02075, the exponent 0.16 as a repeating decimal, minus 1. So P is equal to 0.003429. Our last item to calculate n, in this case, remember, we're looking for the balance at the end of the 5-year term. So our future value, okay, our number of compounding periods is only for that 5-year term. So it's 5 years times 12 payments a year, which equals 60. And just because we have this item given that we haven't written down yet, our last item to write down is that our payment is $641.03. That comes in to step 2. So now I can just substitute these values in, starting with step number 1. So our future value is equal to our present value, 120,000, times 1 plus the equivalent rate of interest, 0.003429, to the exponent 60. Okay, remember, because it's only for the interest term. And if we do that, our future value is equal to $147,360.18. Step 2 now is to find the future value of all the payments we've done to date. So in this case, it's equal to our payment, $641.03, times 1 plus the equivalent rate of interest, 0.003429, to the exponent 60 minus 1, divided by 0.003429, the equivalent rate of interest. And if we calculate this number out, we get $42,623.45. And that number makes sense. That's far smaller than the item in step 1. Because remember, if you go back to drawing our chart, we're here today at time 0. We're looking to translate to 5 years into the future. But your mortgage is 25 years, so you should only have taken a portion out of that mortgage, okay, up to that period in time, okay? So our final step is to take our value from step 1 minus our value from step 2, and that is our outstanding mortgage balance right here at the end of our 5-year interest term. So that's equal to $147,360.18 minus $42,623.45. And if we calculate that out, we get $104,736.73. So now, moving into the future from year 5 to year 25, that is going to be the value that you base your future financing on, okay? At what will likely be a new interest rate that is not 4.15%, okay? Because interest rates fluctuate almost every day. So let's look at a second example, finding balances. So a mortgage for $175,000 is amortized over 25 years. Interest is 3.65% per annum, compounded semi-annually, for a 3-year term, and payments are monthly. What is A, the monthly payment, and B, the balance after the 3-year interest term is ended? So this basically is looking at doing the similar calculations to what we've done in the last 2 examples, just putting them together. So starting with this, again, in these questions, you're going to notice that interest is semi-annual and payments are monthly. So they're not the same as an ordinary general annuity. And what you know is for a mortgage or a debt, the number that's given in the question is always the present value. So you start with your payment formula for part A, okay, looking at using the present value. So your payment is equal to your present value of a general annuity times your equivalent rate of interest, P, divided by 1 minus 1 divided by 1 plus the equivalent rate of interest, P, to the exponent n. Okay? Keep in mind, the value of n for this is the total number of compounding periods looking at this payment over the entirety of the mortgage. Okay? So looking at our side here, our present value in this case is $175,000. Our nominal rate of interest, J, is 3.65%, which is 0.0365. Our number of interest compounding periods, M, is semi-annual, so M is 2. So our periodic rate of interest, I, is J divided by M, or 0.0365 divided by 2, and we get 0.01825. Next, we have to calculate our ratio, C, and that's the number of interest periods divided by the number of payment periods per year. In this case, again, its interest is 2 because it's semi-annual, and payments are monthly, which is 12. So you get the same number of 0.16 as a repeating decimal. So you can now calculate your value for P, the equivalent rate of interest. It's 1 plus the periodic rate of interest, I, to the exponent C minus 1. In this case, 1 plus 0.01825 to the exponent 0.16 as a repeating decimal, minus 1. So if you calculate that out, your equivalent rate of interest is 0.003019. The last item to calculate for this is your total number of compounding periods, N, which is equal to 25 years, because remember, it's the entire length of the mortgage, times 12 payments a year, or 300. So if we substitute these values in, our payment is equal to $175,000 times our equivalent rate of interest, 0.003019, divided by 1 minus 1 divided by 1 plus the equivalent rate of interest, 0.003019, to the exponent 300. Okay? And if you calculate that out, you get a payment of $887.66. Okay? So we'll use that to then look at the balance after the 3-year interest term is ended, and we'll do that on the next slide. So now that we have the payment, okay, I'll just write down the information we had, which was $887.66. Okay? We can now look at the balance after the 3-year interest term has ended. Okay, so remember the 3 steps that we had to do, and they were all involving future value. So step 1 was the future value of your entire loan using compound interest. So future value is in present value times 1 plus the equivalent rate of interest, P, to the exponent n. Remember, n being only, in this case, for the actual 3-year interest term, not the entirety of the mortgage. And step 2, calculating the future value of all the payments that you have to make in this 3-year term only. So that future value, again, I use G for a general annuity, okay, is equal to your payment times 1 plus the equivalent rate of interest, P, to the exponent n minus 1 divided by the equivalent rate of interest, P. So in this case, we can look at these numbers. We calculated them in part A, okay, or most of them. So our payment is $887.66. Our present value is the present value of the entirety of the mortgage, $175,000. Our equivalent rate of interest for this 3-year term, it's not going to change, right? Because the interest rate is the interest rate through the entirety of the term. It's 0.003019. The number that's different here is because we're looking at the end of the 3-year term. Remember, going back to our timeline, we're here today. Our mortgage is 25 years, but we're only going to the end of our term 3 years from now. So our value for n, the number of compounding periods, it's only 3 years times the payments per year, which in this case was monthly. So 3 times 12 gives us a value of n of 36. So this is all the items we need to substitute into these 2 formulas. First formula, the future value is equal to the present value, 175,000, times 1 plus 0.003019, the equivalent rate of interest, to the exponent 36. And if you calculate that out, you get $195,059.81. The second calculation is the annuity, okay, seeing how far our payments have gone in 3 years and what that future value is. And that's equal to our payments, okay, $887.66 times 1 plus the equivalent rate of interest, 0.003019, to the exponent 36, okay, our number of compounding periods, okay, for this 3-year term, minus 1, divided by 0.003019. Okay, if you calculate this future value number out, you get $33,703.30. Again, if you do this in steps, you might get this off by a few cents here and there, which is okay when you're doing your solution for tests. Okay, so now step 3 is to take your value from step 1 minus your value from step 2. In this case, $195,059.81 minus our future value of our payments, which was $33,703.30. And we arrive at $161,356.51. Okay, so that is the value remaining after the 3-year period. Again, you're not going to be surprised that it's not that far off from this first payment. Remember back to when we did amortization schedules. So over a period of 25 years, your payment at the start will be mostly interest and a little bit of principal. And as you get further along paying your mortgage, you end up with more principal being paid off than interest. Okay, you will also you'll start to see that at a certain period in time. So with that, what I want to talk about next, and I'm going to explain it on this PowerPoint, and then I'm going to do a second part to this lesson that shows you how to do these statements in Excel. I can have you do these statements by hand, but I feel it's more productive to show you how to do it in a piece of software like Excel. so you can understand and kind of change it up, or even use something like that in a real life situation if you're looking at refinancing. So a mortgage statement looks at when you actually have monthly mortgage payments from a financial institution. They calculate interest for the exact number of days that have elapsed since your last payment. And remember, months aren't the same. So for example, February has 28 days, March has 31 days, April has 30 days, etc. And depending on where your payments fall, they might fall, let's say on the 27th of a month or the 26th of a month. They may not fall directly at the end of the month. So when they calculate interest, they actually look at the exact number of days that have gone by. So you have to actually do a couple of additional calculations in order to figure out what that interest is, okay, for each one of your payments. Okay, so like I said, they're typically completed in Microsoft Excel. So what I'm doing is I'm going to give you the instructions on kind of what I'm doing prior to showing you in Excel and kind of explaining the math behind it. Okay, so like I said, what we've done so far is find an equivalent rate of interest. Okay, and that has used the same formula, 1 plus your periodic interest rate to the exponent c minus 1. And that gives you the equivalent rate of interest that's calculated for each monthly payment. Okay, that's if all months were equal. Okay, they all have the same number of days. So what you have to do first is you have to go backwards and convert this equivalent rate of interest to an annual rate of interest. And we do that by simply multiplying the equivalent rate of interest by 12, or the number of months in a year. So you're arriving at an overall interest rate for the whole year. So once you have that rate, okay, then what you have to do is find your interest rate for each one of your payment periods. And how you do that is you take the number of days between your payments. Again, it's not going to be the same. It might be 28 or 30 or 31, or if you're late on payments, 33, 34. Okay, it could be more than that. So you substitute this number of days into this formula below. And what you're doing is you're finding a fraction of that annual interest rate. In this case, you're finding the interest rate for only 28 days out of an entire year, which is 365 days, okay? We're excluding in these calculations when it's leap years, okay? So you're going to substitute that in, and I'm going to show you how to do that in Microsoft Excel. And you'll notice that the rate of interest is a little bit different for each interest period. And that's both because every time you make a payment, you're paying off some principal, but it's also because the number of days changes. Okay, so your interest rate for each of those periods changes slightly depending on the number of days that happen in between periods. So like I said, I'm going to go over an example in Microsoft Excel. I'm giving you this example as part of your lecture note. So if you're following along, this is the example that I'm going to do in Microsoft Excel. So have this paper with you when I go over it in part 2 of this lesson, which will be recording my screen, doing it in Microsoft Excel. Okay. So that's it for this part of the lesson. Like I said, part 2, we'll go over the final example, example 5, in Microsoft Excel. So stay tuned.